Okay, so for this video, I'm just going to go over a few of the questions on homework 15 to see if that helps. So, the first one I'm going to do is the polar bear one because it also has an alternate hypothesis question in it. So this says, scientists fear that polar bears are slowly starving due to their shrinking habitat. A healthy male polar bear weighs about 900 pounds. A new expedition was able to estimate the weight of 7 polar bears. They found the average weight to be 161 pounds with a standard deviation of 59. So when I read this, one word immediately sticks out to me. It says that I fear that the polar bears are slowly starving. So if I fear that the polar bears are slowly starving, my null hypothesis, the null, which is sometimes written like this, is always equal to. The null is called the status quo hypothesis, meaning that there's no change from what society just deems reasonable. So they tell us that the healthy average weight of a polar bear is 900 pounds. So my null is every polar bear is 900 pounds. My alternate is what I think is happening. So the null is always equal to, but the alternate is really what we're testing. So if I fear that a bunch of polar bears are slowly starving, then I think that the average is actually smaller than 900. I don't think it's 900 because I think they're starving, so I think it's less than 900. If I said scientists fear that polar bears are overeating due to, human feeding or something, I don't know, then that would be greater, because if they're overeating, I fear that there's a bunch of fat polar bears out there. So my alternate here, the correct answer is the less than, because I fear that they're starving. Okay, let's scroll down. I want to talk about hypothesis for a second. So degrees of freedom is 1 less than sample size. So my sample size is I have 7 polar bears. So if I have 7 polar bears, then my degrees of freedom is 6. So standard error is standard deviation divided by square root of sample size. So the standard deviation was 59 and the sample size was 7. So that makes my standard error, if we said it's standard deviation divided by square root of sample size, then it's 59 over the square root of 7, which is 22.2999. So to 3 decimal places. This is a weird one, so I'd round up to 23.300. But standard error is standard deviation divided by square root of sample size. The t statistic is my sample mean minus the population mean over standard error. The sample mean, when I did the 7 polar bears, if I scroll up, I lose my writing, but you can scroll up and read it. I found their mean to be 861. The mean was supposed to be 900. And over standard error, which we just said, was 22.3. So for my t statistic, I got negative 1.749. So standard error is standard deviation divided by square root of sample size. T statistic is the formula where it's sample mean minus the null over standard error. I'm going to have to make this go away because I got to scroll down. But the T critical with alpha 0.05. So this is where I need to explain for a second. So T critical comes from the T table. If you forget, the first sentence tells you that the values in this table are critical values of T. So the T table is much easier than the Z table that we used first semester. We just need degrees of freedom and alpha level. That's what this is. The decimals up top are alpha level, and the whole numbers on the side are degrees of freedom. So we already said there were 6 degrees of freedom, so I'm looking in this row. It tells me alpha is 0.05, but this is where the explanation we need to talk about. If your alternate hypothesis is not equal to, that means you have a two-tailed test, so that 5% is split into 2 locations. So you would take the 5% and make it 2.5% when you look at the table. Our hypothesis is less than, so an alpha of 0.05 means I'm okay with 5% error. Since I'm only caring about starving polar bears, I'm only caring about the less than direction, the left direction, because if they're fatter than 900, I'm wrong, so I don't care. So I'm only caring about the left side. So all 5% is in one spot, which just means when I go to this table, I'm going to the intersection of 6 and 5%, 0.05. Okay, so my answer is 1.943 for this guy. Now, the last thing we need to talk about is how to actually do the conclusion. Do we reject or do we fail to reject? So to do this, every time I would draw a picture. So we have our normal curve, and on this, the middle is always 0. Always. My T critical is positive and negative 1.9, but since I care about starving polar bears, I'm on the left side. And numbers to the left of 0 are negative. Okay, so I'm worried about the left side, so I shade to the left. And then I'm trying to locate my T statistic, which we said was negative 1.749. So now I've got to figure out, is negative 1.7 out here or inside? So the critical value is negative 1.9, negative 1.7 is inside. If it is inside, we fail to reject. If it is out in the shaded region, we reject. Because this out here is called the critical / reject region. So if it falls further extreme than the T critical, further outside, that's in the critical or reject region. However, ours falls inside the curve, not in the critical region. So since it is not in the critical region, we fail to reject. The actual answer to the question is, remember that the null hypothesis is equal to 900. If we fail to reject this, then that means we're basically saying we like this. If we reject it, we're saying we don't like this statement. But we failed to reject that the average is 900. Therefore, there is no evidence that it is less than 900. Because we failed to reject, we just say there's not enough evidence to reject it. Therefore, they are what they're supposed to be. They are 900. And that's how every t-test works. Is you're going to find t-critical, you're going to find t-statistic, and then you're going to say, do I reject or fail to reject based off these two values, t-statistic and t-critical. Okay, the last thing, and I'm going to do this much faster because I don't want you to have to watch an hour video, but is confidence intervals. The test is over. Can you do a t-test and can you do a confidence interval? So all the t-tests look like what I just did. And another reason I want to do confidence intervals is all confidence intervals are two-tailed because you have an upper and lower bound. Because remember, a confidence interval, you're estimating the average of something, and when if your boss asks you what's the speed of light and you don't know it, you have to test for it, which in this case we're studying for the speed of light. You're going to say, well, I don't know 100% accurate what it is, but I'm 95% sure that it falls between these two numbers, which is what a confidence interval is. So the first thing it asks us to do is standard error. We just did standard error. That's standard deviation divided by square root of sample size. So it tells me the standard deviation is 107.12 over sample size, which is 23. So when I do that, I get a standard error of 22.336. Okay, so keep that in mind. Then we're going to generate a 95% confidence interval for the true speed of light using Michelson's data. So 95% confident, that means I'm okay with 5% error. So when I look at my t-table, I'm okay with 5% error, but since all confidence intervals are two-tailed, we need to take this 5%, split it among each tail, so I'm actually going to look at the 2.5% column. Okay, I was going to look at the 5%, but since it's two-tailed, I scoot over to the 2.5%. And we did 23 trials. So since we did 23 trials, my degrees of freedom is 22. So we're going where 22 meets 2.5%, which is 2.074. So make sure if it's a two-tailed test that you split the alpha in half. So 22, 2.5% is 2.074. Now, margin of error is t critical times standard error. Well, we just did t critical, which was 2.074. And we just did standard error in the previous question and got 22.336. We multiply those guys together, and we get a margin of error of 46.325. Okay, so margin of error is just standard error times the critical value of t. So you do that, and then now we can actually do our conclusion. So lower and upper bound. So remember, we're going to say that we're 95% confident that the speed of light is between this number and this number. That's what we're doing here. The speed of light is between this number and this number. So how we do that is we say we found our sample mean of 756.22. So the confidence interval on your formula sheet will say x bar plus or minus margin of error. X bar is the sample mean, so it's 756.22 plus or minus margin of error, which we said was 46.325. The lower bound is just when you subtract, and the upper bound is when you add. So the lower end estimate is 709.895, and the upper end is 802.545. So basically, what we're saying here is our conclusion again with confidence intervals is I am 95% confident that the speed of light is between 709 and 802 kilometers per second. Okay? That's all confidence interval is saying is I'm not 100% sure, so I'm going to hedge my bet a little bit. And I'm going to say that I'm 95% sure that the correct answer falls between these two numbers. So I said it was between, we said it's between 709 and 802 was our confidence interval. So if the true speed of light is 710, did my experiment work? Well, I said it's between 700 and 800, basically. So since 710 falls between these two numbers, then yes, my experiment was a success because my confidence interval captured the correct answer. Okay,